Let's work some of these problems involving tests of hypothesis. And remember, what we're trying to do here is reject a status quo in favor of an alternative or research hypothesis. So we set up a status quo which is H0, so there's the 0, and that corresponds to the null hypothesis is what we call it. And we're trying to reject the null in favor of the alternative. To do that, we need to take a sample, a random sample, from the population, and that mean has to fall into a rejection region, either greater than, or if we're trying to prove that the alternative is less than the null, then it has to be in this rejection region. And this little shaded area is what you might call the benefit of the doubt. So here's the null hypothesis, the status quo, and then we give them the benefit of the doubt because there's some randomness involved in sampling. But if we're out here, then we're 90 or 95% or 99% certain that it's pretty rare to get a sample that falls in these regions. That's the idea in test of hypothesis. You should write down these numbers corresponding to these tests, lower-tailed, upper-tailed, two-tailed. These are the ones we've been working with quite a bit in confidence intervals. So these numbers should look familiar to you. These maybe not so much. So write these down, because I'll always, and you'll probably always see 90% or 95% or 99%. In businesses, sometimes we see 99.999%, Six Sigma type tests. Always draw a picture. So when you do these problems, here's some problem, 6.8 is a good one, where you're drawing a picture to correspond to the null hypothesis in the rejection region. So for this z greater than 1.96, you would draw a picture and it would show the outer area. So I'll do it real quick. These are all pretty easy, but always draw a picture. So here's your normal curve, mostly normal. Here's your null hypothesis, status quo value. If we're trying to prove that something is actually greater than this null, then we have to get out here. This is called alpha, and this is 1.96. So we'd have to find a z that's greater than 1.96. Same way here, and this corresponds to a alpha of 0.025. Let's see, so the same thing with 1.645, it's greater than, all these are greater than, and you just draw them the same way. Here's one that's less than, and so you draw your curve, and you'd have to be over here where this is negative 1.28. So you would do the math, and if your z value was found to be over in this region, then you could state at a 90% level, that confidence level, that you could reject the null hypothesis. So always draw pictures, practice on these. Here's some practice involving setting up the null hypothesis. So in this little example, it's the effectiveness of online classes. And what we're interested in is this person states that 60% of college presidents believe that their online education courses are as good as or superior to courses that use traditional face-to-face. Give the null hypothesis for testing. So the null hypothesis is that it's 60%, and we want to prove that no, it's not 60%. So the null hypothesis is 60%. The alternative is no, it's not. It's either less than 60 or greater than 60. We use a z-score of 2.575, either above or below. So if you drew a picture here, this would be 0. On another scale, this would be the 60%. And we want to show via some sample that the sample either falls over here or over here. And this number would be 2.576 and negative 2.576. So if it falls in this region, if the sample we take, the sample mean falls in this region, then we reject the null hypothesis in favor of the alternative. The alternative is, no, it's not 60%. So that's how you do these problems. You have to set up the status quo and then prove that it's, given the benefit of the doubt, then prove that it falls outside. And if it doesn't, then you cannot reject that null hypothesis. That's the idea. Here's one for PGA Golf of America. They're saying that the golf facilities participate on average $2,400 in green fees. Lessons or equipment expenditures. A teaching professional golf club believes that the average gain in greens fees, if you give these free 10-minute lessons, is more than $2,400. So the null hypothesis, the status quo, is that it is $2,400. So here's the null on another scale. That's $2,400. That's the null, and so it could be less. Could be all this. Could be less. To prove that it's more, we have to take a sample and it has to fall out in this region there. At whatever confidence level we're interested in. So if it's 5%, this would be 1.645. So always draw a picture. That's how these things work. Here's another interesting one. This deals with juries in our legal system. And the idea here is that you're assumed innocent until you can be proven guilty beyond a reasonable doubt. So that's what we're trying to do with this statistical testing, test of hypothesis, is you're assuming something, and then we have to show beyond a reasonable doubt that that status quo is not reasonable. Let's do a couple more quickly. You should write these down in your cheat sheet because this is what we're going to do. This is how we're going to be working these. We're going to set up a null hypothesis. So this is the mean, this is the status quo, the mean of the status quo. And then we want to take a sample, and based on this sample, so we're dealing with large samples, by the way. Based on this sample, we have a sample mean, and that's a sample standard deviation, and then that's the sample size. So we'll use this formula to create the z statistic, and then we will compare this z statistic to that we've computed for or set up for our test, based on whether it's a one-tailed test, so it's less than or it's greater than. That's the alternative, is less than or greater than. Or a two-tailed test where you just say, it's not equal to. That's the idea. Let's work a couple of these, and then you should work these on your own. The more you work, the better off you'll be, the better you understand them, because they're all pretty similar. They're all pretty basic, and the same ideas are being used in a lot of them. So here's a problem. You're interested in conducting a test where the mean is 255, that's the status quo, and the alternative is, I think it's more than 255. And you've decided that if it's more than 270, then you can reject this status quo that it's 255. So you're giving them the benefit of the doubt. This is based on a sample. So what we want to do is draw a picture. We'll draw a picture here. And here's our null hypothesis. On another scale, this would be 255. And we're saying it has to be 270 to reject. What does that 270 correspond to? Well, that 270 corresponds to a z value that you calculate by saying z equals x bar minus mu naught over the sample size, the standard deviation, which is 63, divided by the sample size, which is, what is the sample size? Oh, it's 81. Where do we see the sample size? Oh, there's 81. Square root of 81. So if you did this math, this would be 270 is what we have to measure, minus 255 over this. And this would come out to be 2.14. So this z value is 2.14. So if we take a sample and it's greater than 2.14, then we can reject. Or we could also say if we take a sample and it's greater than 270, we could reject. So that's the idea. That's the idea. That an alpha is the probability of making a type 1 error. So we'll do one more. Here's a random sample based on 100 observations, so n equals 100. Standard deviation of 60 for this sample, and the sample mean was 110. You want to test the hypothesis that the mean is actually 100 against the alternative that, no, I think it's greater than 100, using alpha equals 5%. So that's the idea. That's what we want to do. So we'll draw a picture of this. I'll draw a picture over here. Here's my normal curve. There's my null hypothesis. The null hypothesis in this case is 0. On a different scale, it's 100. So the mean equals 100 is what we're testing against. And we want to say, no, I think it's greater than 100 at this rejection of alpha equals 0.05. And if you look it up in the table, that's 1.67. So if we calculate and do this, sorry, it's 1.645. 1.645. I just looked it up in the table. It's 1.645. So if you do the math on this, the z is equal to, we got 110. That's given there. That's what that was the sample, and this is the status quo, and the standard deviation was 60, and the sample size was 100. And if you do the math on that, it comes out to be 1.67. And 1.67 is bigger than 1.645, so we reject. We say, no, I think it's bigger than this sample of 110 shows that we can reject the hypothesis that the mean is really 100. And let's see, the other part of this deals with a two-tailed test, to where we say, I think it's, tested against the hypothesis that it's not equal to 100. So we're pretty close here, by the way. And what we're going to find out is we can't reject this one. So we'll draw a picture. Here's 0. This corresponds to 100. And the two-tailed test is going to be a little bit further out here. These areas are a little bit further out because this was all on one side. Now I'm spreading them out on two sides. And once again, I get the same number of 1.67. So the number is 1.67. But this value here for the rejection region, this is 1.96 and negative 1.96. So this number that we calculated falls right about here, and this is the fail to reject. And so we cannot reject the null hypothesis when the alternative is, no, it's not equal to 100. If we just say, I think it's greater than 100, this is a little bit easier test, especially if we know we're not going to get down here. We know it's going to be bigger. So work a lot of these problems and you'll get the idea of how these tests work. It's pretty straightforward. You have to calculate the z statistic, draw your picture, and figure out what the rejection area is.